Hi there, welcome to this second in the videos with regards to the initial steps for cable sizing. Previously we selected a 6mm squared cable for that 3 kilowatt load on the 20 metre run of twin and earth, 2-core and earth, PVC sheathed cable, so flat twin and earth. So now we're going to look at the voltage drop calculations for that installation. So there are two methods in which we can carry out volt drop. First one we're going to look at is the one that's identified in Appendix 4, Section 5, Paragraph 2 in writing. It's the second sentence in that paragraph, where we can take the permissible voltage drop, be that 3% or 5% on a 230 volt system if there's no distribution circuit. And then divide that by the design current multiplied by the length, and that gives you your maximum millivolt per ampere per meter value that can be tolerated. So the previous circuit was an immersion heater, 3 kilowatt immersion heater. 5% of 230 volts is 11.5 volts. That's the maximum permitted volt drop that we can allow. So the design current for that circuit was 13.04 amperes, and the length, as we identified in the last question, was 20 meters. We now need to work out what's the maximum volt drop that we can accept. Okay, so that then helps us select the minimum size of cable. So from the information we have, we can take that 11.5 volts, that maximum permissible volt drop, and we can divide it by 13.04 amperes, okay, times 20, times the 20 meters. That gives us 0.0441 volts per ampere per meter. If you look in that table that we were looking at earlier, table 4D5, you'll see that at the end column, it's in millivolts per ampere per meter, so we need to multiply this by 1000 to get our millivolts per ampere per meter value. So that's a maximum millivolt per ampere per meter value of 44.1 millivolts per ampere per meter. So down this right hand side column, you'll see there in column 9, the first cable, a 1mm squared cable, its maximum, its millivolt per ampere per value, millivolt per ampere per meter value stated is 44 millivolts per ampere, which is less than the 44.1 millivolts per ampere maximum that we can allow. So using this method, a starting cable that we could think about selecting would be a 1mm squared conductor. Okay. Now, most designers, when they design an installation, this is the first step that they identify or they carry out, so it gives them a starting point for their selection process. However, when I carry out a cable size calculation, I look at the overload side of it first. I make sure I'm not going to burn the property down rather than making sure the piece of equipment works. Okay, so first thing I do is I do that overcurrent calculation, the overload calc, making sure that the cable's not going to have any or too many hot spots in it under overload conditions. This method here, as I said, we selected in the last question, we selected a 6mm squared conductor. Okay, 6 times the size of the minimum that will actually make that 3 kilowatt immersion heater work. Now, if you turn that on, the immersion heater would work. However, particularly where we run through that thermal insulation, you would be sitting there going, have we got a cat? Because you would start to smell the plastic burning. Might not necessarily burn initially, but the circuit would not last its planned 25 years. Okay, so a 1 millimeter squared cable using that designer, what we class as a designer method, to work out the maximum millivolt per ampere per meter value that can be tolerated, gives us a 1 millimeter squared cable. It brings us just under that 11.5 volts maximum volt drop for that 5% volt drop. Okay. Now, the method that I prefer, the one that's embedded in the process, if you look in part 6 in appendix 4, or section 6 in appendix 4, you'll find this in section 6. So we take the millivolts per ampere per meter value from our selected cable, multiply it by the design current and the length, and then divide it by 1,000, and that gives us the actual volt drop. We'd check that then, that actual volt drop then against the maximum permitted. Okay, so looking at that table 4D5, the cable that we selected was a 6 millimeter squared cable for overload protection in the previous calculation, or in the video prior to this one. That gives us a 7.3 millivolts per ampere per meter value for that conductor. Okay, so we're going to utilize this value in the calculation. So the volt drop, the actual volt drop, okay, plug in the numbers. We take that 7.3 millivolts per ampere per meter and we multiply it by that 13.04 amperes for the design current, okay, from the previous video, times the length of the run, which is 20 meters, and then we divide it by 1,000. Why are we dividing it by 1,000? Well, this value here is in millivolts per ampere per meter. We need to find our answer in volts. So the actual volt drop that we have for this circuit is 1.9 volts. Okay, so that passes the maximum volt drop of 11.5 volts. That's the basics of volt drop calculations, folks. You will have examples in your folder. If you're on any difficulties, you know how to get in contact with me.